Welcome back to Chapter 3. And in this part of Chapter 3, what we're going to do is we're going to be taking a look at what we did with our vectors and breaking it apart into pieces, along with our analysis of motion from Chapter 2, to now look at a new special type of motion called two-dimensional motion. Now we're actually going to try and turn. We're not going to go right or back and forth anymore, straight forward or straight back. Now we're actually going to turn. And this is actually a motion called two-dimensional motion. And it turns out that many objects will remain in the same plane, which means on the same flat part that they're in as they're in motion. So what they're going to do is they're going to move up and down and forward, but not side to side. If you add in that side to side part, now it becomes three-dimensional motion, which gets a little more complicated. We can still do it, but again, we're going to start with the simplest case and then work to the more complex. We're going to use the Earth, as always, as our reference frame. So we're going to say that the Earth itself is stationary, and we're going to measure that motion with respect to the Earth. Our biggest one that we're going to look at is called projectile motion, okay? And projectile motion is where we're headed, but in this two-dimensional motion, we're going to use the fact that these vectors, our ability to break apart vectors, along with our distance and displacement, velocity and speed and acceleration and time, all of our kinematic equations, to now analyze the motion, not only as it goes up and down, but also as it goes forward and back. Okay? So the fact that we can break apart vectors into perpendicular pieces allows us to now use that along with our kinematic equations in order to analyze the motion of an object. Okay? And again, the key thing is that these pieces, the horizontal and the vertical, can be analyzed separately. I can't write. You get the idea. Sorry. I apparently cannot spell the word separately. I apologize. Okay. So we're just going to be doing everything we did in Chapter 2. But now we're going to be doing it in two different directions. So we'll be doing it both horizontally and vertically. And it's the combination of those motions that allows us to plot out where an object moves as it moves through space. Okay? And an example of this independent motion is the thought experiment. We'll talk about this more in detail, but just take a look and pause the video here for a second and think about this. Okay? Just take a minute. You have a bullet, and if you shoot it straight, fired parallel to the ground, at the same time you drop one from the exact same height, which one hits the ground first? Think about that. Pause the video and think about it. Okay, welcome back. Hopefully you have an answer, but it turns out it's actually that they will hit the ground at the exact same time. And tomorrow in class, I want to show you a video where Mythbusters actually did this to prove this. Okay? This is a special case called projectile motion. If an object is shot, so let's say here is I'm just going to make a ball for right now. That object has an initial velocity here. This object will fall down. And as it falls down, we know, we've dropped stuff before, it's going to have this as its vertical motion. And we can analyze that because we've done this before. But as it's falling, it's also going to be traveling forward. So here, oops, sorry, I'm going to change colors. This is its horizontal motion. And by combining these two together, and I'm going to put this in a light blue, what happens is as it falls, as it moves forward, it begins to fall. So now it becomes here, and now it's here, and now it's here, and now it's here. And so its path as it falls is a parabola. And this will follow a parabolic path. Now this is if I shot an object horizontally. If I were to throw an object straight up in the air, and we'll look at both of these cases. But if I were instead to shoot an object up in the air. So here's my object here, and I give it an initial velocity up. And I give it a horizontal velocity over. We know that from an object we throw up, it's going to go up as high as it can and then come back down. We've seen this before. Horizontally, it's going to be moving forward. And so if we were to plot this out, this object would go here, and here, and here, and here, and here, and then start to come back down again. I'm putting in the dots in the wrong spot. But it would follow a full parabola. And so by breaking apart this horizontal and this vertical motion independently, we can actually see where the object is going to be horizontally with respect to time and vertically with respect to time. And by plotting that out, we can actually show that. And so if I take this pen and I throw it like this, hopefully you can see that on screen. If not, I'll show you tomorrow in person as well. But that is moving through a parabolic path. And so the easiest way to analyze these problems is by using a chart, okay, and analyzing the horizontal and the vertical motion differently. And so this is the chart as we can see it. And again, we'll practice this tomorrow. You're going to break this up because the horizontal and the vertical are independent. We can analyze each motion, and we can find out horizontally, we can find out the distance that it travels. And we know its initial velocity, and we know its final velocity, and we can figure out its acceleration. And vertically, we can know its position, its distance, displacement, its initial velocity, its final velocity, and its acceleration. Now, because these two are independent of each other, very, very important, you're going to hear me talk about this tomorrow as well. This line cannot be crossed. And what that means is that your vertical distance is not going to be affected by the horizontal initial velocity. Your final horizontal velocity is not going to be affected by the vertical acceleration. And so to help me keep them independent of each other, I like to put subscripts on my subscripts. And so instead of just having D horizontal, I'll write that as a dx. So the distance in the x direction, the initial velocity in the x direction, the final velocity in the x direction, and the acceleration in the x direction. The initial velocity, sorry, the distance in the y, the initial velocity in the y, the final velocity in the y, and the acceleration in the y. Now, you'll notice I have left one thing off. In all of our kinematic equations, we've also had one other term here. And that's because the thing that I left off is time. And time is the only thing that is the same for horizontal and vertical. Because if you stop and think about it, if I throw something up in the air, it's going to stop moving forward when it hits the ground. And so the time it takes for it to go up and back down is going to be the exact same as the time it takes for it to go forward. And so the time is the one thing that can be used on both sides. Once you know these things, and we're going to fill this all in, once you know these, you can use this chart along with our kinematic equations to solve and plot where the object is. What is its maximum height? Where is it at this particular time? How far forward will it go? And we're going to do a bunch of these sample problems over and over again tomorrow. So this is called projectile motion, and we will do this a lot. Okay? Now, I don't want to talk about this. There are a couple special cases, and we'll talk about this briefly, because I'm going to finish off the chapter today, and if we have to, we'll give you the tomorrow off and taking notes in the evening. If you have an object that's fired at 45 degrees, that is when you get maximum range. And if I were to just plot this out, if I were to shoot something up, okay, if I were to shoot it completely, like here's the ground, like this. If I shoot it at like a 10-degree angle, it's going to go like this. If I shoot it at a 30-degree angle, it's going to go up and come back down like this. I shoot at a 45-degree angle, and I'll put this in red, it's going to go up and then come back down here. Okay? But if I were to shoot it at a 60-degree angle, it's going to travel up in the air more, but it's not going to go as far forward. And so this 60-degree angle and this 30-degree angle is actually going to give you the exact same range. Now again, this is in the absence of air friction. If I were to do an 80-degree angle, it's going to go up really high, but then come back down. And so this 80 will be the same as the 10. So you're going to get maximum horizontal distance at 45 degrees. And we can demonstrate that. I'll show you that a little bit tomorrow in a video as well. So that's for maximum range, max range. And then if you want max height, obviously you're just going to shoot it straight up. So that's got to be at 90 degrees. Okay? Now, we've already talked about frames of reference before. Okay? We still use the Earth as our frame of reference, but the other thing we do is we use a Cartesian coordinate plane. And so we will, in all of these problems, use our Cartesian coordinate plane where this is your x-axis, this is your y-axis. If you're above the x-axis, we're going to target it as a positive y. If you're below the x-axis, then it's going to be a negative y. If you're moving to the right, positive x. If you're moving to the left, it's a negative x. And so those are just some kind of conventions that we use just to have at our own purposes. All right, so this is the end of Chapter 3. We're going to do a lot of sample problems with this because this can be a little bit tricky to try and get through and to finally use the chart. But we'll talk about it more in great detail tomorrow. So everybody have a great night. We'll see you later. Bye.